Hello, welcome back. This is Professor Lenis here. I decided to change the recording format. So from now on, I'm going to place this recording in a different place on the Blackboard, and I'll let you know. I want to build content. So there will be basically on course content. I'll give you detailed instructions. I'll send an email to you. I want to start this one with reviewing some equations that I promised to write down from the law number 1, chemical equilibrium. So let's go through all these equations. And then if you have questions, please don't forget to send me an email. All right, so here we are. These are the equations that we work on in the lab. The ones that I was supposed to write it down for you. I must congratulate all of you who sent already the lab reports. Only a few didn't send the report yet, so you still have some time. You haven't done so. Also, congratulations to those who didn't want to wait for the chemical equations. They found it out and they did it already in the lab report. Very good job. That's a proactive approach. All right. These equations refers to the part where we work with complex ions. The purpose of this part of the lab is to compare the behavior of 3 metals: zinc, magnesium, and copper. And we compare this, the behavior of these metal compounds when they react against acid or base. We're going to find basically 2 aspects of this behavior. And the question is, what is the character, acid-base character of these metals? Means, do they behave as acids? Can they behave as bases? Can they behave as both acid and base? So that's one part. And the second part is, can they make metal complexes? Can they form metal complexes? We'll see. That's why we reacted the aqueous solution of these metals with 3 reagents. Initially, sodium hydroxide, and then hydrochloric acid, and then we added extra sodium hydroxide. That is an excess of sodium hydroxide, and then reaction with ammonia. So let's start with zinc. Remember also that I was mentioning in the lab how important is to recognize the position of these metals in the periodic table. According with their position in the periodic table, we can describe zinc as a transition metal. It belongs to the 3D group. It's a deep black in the periodic table. That means zinc is classified as, or at least is, in the group of transition metals. However, zinc have a very special behavior, as you will see through these reactions. Even though zinc is a member of the 3D block of the periodic table, zinc cannot form an ion with an incomplete d orbital, and therefore is not a true transition element. Zinc forms only compounds in its +2 oxidation state. So as you can notice here on the writing, zinc is working here as +2. That's the oxidation number for zinc in the compound. And all zinc compounds will be with +2. You see the difference? Usually transition elements have more than one oxidation state. They do electronic transition between the d orbital electrons and upper s orbital electrons. So this electronic transition produce a photon, a colorful photon. They emit light in the visible area of the spectrum. So that's a characteristic of transition metals. But as you can see, zinc here it has only +2 oxidation number for most of its compounds. Also, zinc compounds are usually white, and the solutions of zinc are aqueous solutions of zinc compounds are clear, colorless. So that's interesting behavior for a transition metal. That's why in general we say zinc is not a true transition element, at least doesn't behave as normally will do as any other transition element. However, zinc forms complexes. So as not many as other transition metals, but it does, it forms some complexes, and we are going to see a couple of those complexes formed by the zinc ion. All right, in our experiment, initially we have zinc nitrate. We started with the zinc nitrate because zinc nitrate is a soluble compound, so we dissolve in water. We have aqueous solutions of zinc nitrate, and as you can remember, we added zinc nitrate solution into 3 test tubes. To each of these test tubes, we added a strong base. Usually we use sodium hydroxide, which is strong base, or we can use potassium hydroxide as well. So we added a few drops of strong base, sodium hydroxide, to the aqueous. And what did you see? What do we get here? You can go and check. You can stop here, go and check your notes to verify, to remember what happened after we added sodium hydroxide to the zinc nitrate, zinc 2 nitrate solution. And yes, it forms a PPT. What is a PPT? It's a precipitate. That means these reactions form something that is not soluble in water. So it forms a solid. And that solid is zinc 2 hydroxide. That's why we write it here, S. Sometimes we write an arrow pointing down to show that it's a precipitate, it's a solid that forms in the solution and settles down. And here we have the byproducts. We are not interested in these byproducts, so most of the times I will refer only to the main product, the one that is making a change there, plus water. Liquid. Once we get this precipitate on each test tube, we are going to add 3 reagents. So here we have this one, it's being produced, and it's this one, which is a solid. The first reaction is with solution of hydrochloric acid. It's aqueous. So we know this is acid, this is a strong acid. Here we see hydroxide, so it makes sense to think, okay, this is a base. That makes sense. It's hydroxide. Hydroxides are bases. And this is the acid. It's a strong acid. So we'll have acid-base reaction here when they react each other. What did you observe? Remember the observation after this? What happened with the solid? What happened with the precipitate? It disappeared. Why? Because this reaction makes a soluble zinc 2 chloride. So we can write here, it is aqueous. What is the byproduct? OH plus H plus will form water, liquid. How many of those? We need 2 chlorides, so that means we need 2 here, and that will form 2 waters. All right. This is the soluble chloride. That's why you see the solid disappears. It's gone once you add the acid, because forms a soluble zinc 2 chloride. So we say this is zinc 2 chloride. And here it's clear that we have acid-base reaction. So zinc 2 oxide behaving as base, and of course hydrochloric acid is a strong acid. The next reaction is on the next tube that contains this also, formed during the first step of the experiment. So this comes from here, and each of the 3 test tubes have this precipitate. How do you recognize the formation of precipitate? Because they form usually cloudy solutions, milky, or it depends on the color of the ion, the emission during the electronic transition of the ion during the reaction. And also you recognize the formation of precipitate because it's a solid. So on the second test tube, we have zinc 2 hydroxide solid, and we added more sodium hydroxide. So that's why we say we are adding an excess of sodium hydroxide. We added more. In the first step, we had the nitrate, we added the hydroxide, and we get the hydroxide. Now we are going to add more hydroxide to that one. What do you expect to happen? Common sense says that if in the first reaction we add a few drops of sodium hydroxide to the soluble zinc nitrate and form the insoluble zinc 2 hydroxide, then we expect to get even more solid when we add more sodium hydroxide. So we added one more drop, it forms more precipitate there, yes. Then we add another drop of sodium hydroxide to this solid, and yes, we get more solid, more precipitate. That makes sense because here we have a amount of the nitrate which is soluble. We keep adding sodium hydroxide to react with this zinc nitrate which is soluble, and will make more solid, more precipitate. But at some point, we add sodium hydroxide to this one, and this one will run off. It's gone. All of them now is reacted with the sodium hydroxide because we keep adding this drop by drop. And after that, the next drop added, after the next drop was added, what do you see here? Suddenly, that precipitate disappear. How is that possible? First, the soluble reacts with sodium hydroxide to form a precipitate. You keep adding sodium hydroxide here, and you get more precipitate. It's reacting with this. Add one more drop of sodium hydroxide, this one keeps reacting to make the solid, making more solid. But at some point, this is going to run off. All reacted with the excess of sodium hydroxide solution. Yeah. The next drop will react with all the precipitate. So zinc to hydroxide, and that will produce something different. A soluble compound, because the precipitate disappears. So that means something there inside the tube is soluble now, suddenly. It's like there was a reversal of the behavior. Now, the zinc is going to behave in a different way with an excess of sodium hydroxide. What compound is that? That's what we call a complex. Let me write the complex first. So it will be zinc here. We write complexes in square brackets. When you see a compound in a square bracket, that means you have a complex. This case is a metal complex, OH, here, 4. Now we can close it. Remember OH, ion, hydroxide ion, has negative charge. So we have, and zinc is 2+, right? That's the oxidation number of zinc. So we have 2+ and 4 minus. OH is minus times 4. So we have 4 OH minus. What is the total charge here? Let's do that. Let's do it here. All right, so zinc is +2. OH is -1 times 4 is going to be -4. So +2 minus 4 gives you -2. That's the charge of this complex ion. We should put red here because we're talking about the charge of the ion. -2. And this is aqueous now. Aqueous is soluble. That's why you see this zinc 2 hydroxide being dissolved. This is a hydroxide, which is solid, it's insoluble. And here, since this is in a square bracket, it's not hydroxide, it's a complex. Also notice that there was no change in the oxidation number. Oxidation number here for zinc is still +2, as I mentioned initially. So there is no change in the oxidation number. There was no change in the oxidation number of the hydroxide, it's still -1. So this is not a redox reaction. This is just a replacement or addition, in this case, addition of the ligand here to the complex. And the shape of this complex is square planar. This is a square planar compound with coordination number. Coordination number for this complex is 4. That gives the square planar shape for the complex, which is soluble. Now, since the whole ion has -2 charge, so we need to balance that with the spectator ions. So it makes sense if we write here Na2. This is plus, 2 plus, plus times 2 is 2 plus. Yeah, that balance out the negative charge. So it is electrically neutral. The second analysis we can do here is how is this compound behaving here when reacts to forms the complex. So we have, I'm going to write it here again, zinc hydroxide. This, remember, zinc hydroxides are insoluble. They don't dissolve in water. So it's solid. Once this is fully formed, and you add an excess of sodium hydroxide, this is a base here. If this is a base, then, and there was a full reaction because we noticed the change, it's actually reacting. The base, well, the hydroxide reacting with this strong base to make something new, a complex. So we call this a metal. If you don't remember from your Chem 11 what is a metal complex, I will suggest go and read a little bit how metal complexes are written and how to name name complexes. This is a complex tetra hydroxo zinc Kate 2. The oxidation number is 2. Tetra. Four hydroxo H zinc Kate. So yes, we are in a base to this hydroxide. So if you add a base to a hydroxide and that actually forms a reaction, that means this is reacting or is working now as an acid-base reaction. So the base is acting as acid when you add an excess of base. Here the base reacts with acid. The hydroxide reacts with acid, therefore behaves as a base. And this actually forms a new compound. There's a reaction. Here also there's a reaction. So that means the base, the hydroxide here behaves as a base against hydrochloric acid, and the hydroxide behaves as an acid against a strong base. That particular behavior, when a substance can behave as base or acid, they have a special name. We call this amphoteric compound or amphoteric properties. Amphoteric. I'm trying to write it here. Amphoteric. Oh, cannot do it that way. I don't have the skill. Okay. Let's put it. So zinc here is behaving, has a property called amphoteric. Or we can say zinc is amphiprotic. Again, means zinc can behave as acid or base. All right, the next reaction is with the same insoluble hydroxide against ammonia. What happened there? Ammonia is also a base. It's actually a weak base. You can write it here. Ammonia is a weak base, as opposed to sodium hydroxide, which is a strong base. So let's see what happens when we react the zinc 2 hydroxide with the weak base ammonia. It's aqueous. So we have ammonia gas. Ammonia NH3 is actually a gas. We can dissolve down water and we have aqueous solutions of ammonia. So it's not normally we write as NH3, NH3, you can write it that way, that water. Like that. That's ammonia. Okay, it's reacting water. Sometimes you can see it like this one, NH4 OH. Notice that this is the same. This species, ammonium hydroxide, is sometimes better to express it this way. Okay. So what happened there? What happened with the solid? Did the solid disappear here? Was there a reaction? That's an indication of reaction. If the solid disappeared, that means there was a reaction. So what did you see? Disappear, right? Why? Because it forms another complex with ammonium. Zinc, NH3, 4. And what is the oxidation number now? What is the oxidation number for this? This is 2+. And what is the charge of ammonia here? Ammonia is neutral. It's neutral, no charge. Yeah, no charge. So what is the total charge for the complex? It's still 2+. The 2+ from zinc. 2+. Plus from here, ammonia kicks out the OH, so we got 2 OH minus. Again, this is not redox reaction. This is just displacement of ligand. This is a ligand. Hydrox. When you go and read about metal complexes, you will learn about ligands. All right. So, and this is soluble. Oh, sorry. Aqueous, soluble. Aqueous, is soluble. Dissolves in water. So that confirms that zinc can form metal complexes. That zinc has a amphoteric behavior. It is an amphiprotic compound, forms amphiprotic compounds. 2 big conclusions out of this first experiment, of this part of the experiment. The next one is the reaction of magnesium compounds. What is the position of magnesium in the periodic table? Magnesium belongs to group 2 of the periodic table. So belongs to the S block of the periodic table, and we call this a representative element. That means from there that magnesium must show oxidation number +2. Always. It's not a transition metal.
Same oxidation number as zinc, but let's see how is the behavior. First reaction. So we have this solution into 3 test tubes. 1, 2, 3. Each one has magnesium nitrate, which is aqueous, colorless solution. All nitrates are soluble. Magnesium makes clear, colorless aqueous solutions. When they are soluble like this. And to each of those, we added 1 or 2 drops of strong base. What do we get? We get a precipitate. Yes, what precipitate is this? The magnesium hydroxide. Magnesium hydroxide compound, which is solid. We can complete the equation. If you notice the equation is unbalanced, you can balance it. Let's try to balance it now. So what is next? So we have the nitrate here. So we should get to NaNO3, the sodium nitrate, which is, of course, aqueous. Aqueous there. All nitrates are soluble. This hydroxide. Usually, metal hydroxides are insoluble, especially group 2 and transition metals hydroxides are insoluble. All group 1 metals hydroxides are soluble. All of them. All right. So we get the insoluble magnesium hydroxide. Notice that I'm not saying magnesium 2. There's no need to say magnesium 2 hydroxide. No, we just call this magnesium hydroxide. Notice that on the first one, we call this zinc 2 hydroxide. Why? Because this is a transition metal. On transition metals, we need to, using the stock rules of chemical nomenclature, we need to write the oxidation number of the transition metal using Roman numbers between parentheses, and no space here between the name and the oxidation number. Although we say that zinc is not true transition metal, but it's classified as transition metal because it belongs to the D block of the periodic table. Okay. So the next reaction, is here. Once we get the insoluble hydroxide, which is this solid here, so we have the precipitate here. Precipitate, it's milky, cloudy, nice white precipitate. And the previous precipitate we think was kind of gelatinous precipitate, but this is clearly solid. You can see this solid pieces here on each test tube. Now, to the first tube, we add hydrochloric acid solution, aqueous. So we have hydroxide and acid, strong acid, to see the acid-base reaction, and we know the acid-base reaction always forms a salt and water. Do we get that? Yes. So we get Mg, Cl2, soluble, aqueous, plus water in this case, liquid. How many of those? 2 here and 2 waters. So it's soluble. So yes, there was a reaction, this acid-base reaction. That means this is behaving as a base. It's silly to say, right? Because obviously it's a base here, it's OH minus, it's hydroxide. So they should behave as a base. But we have to say that because remember the previous experiment, that base behaved actually as an acid. Here, this is behaving as a base, and this is behaving as an acid. So depending on the environment, this may or may not change this behavior, basic behavior. Here, clearly, forming a new compound, this is behaving as a base. Now, let's add an excess of sodium hydroxide to the second tube. What happened? Did they disappear? Did the solid disappear? Did the precipitate disappear? What did you see? Check your notes, stop and check. Don't wait for my answer. Be proactive. Put your brain to work. The precipitate didn't disappear. So initially, the next trap, it makes more magnesium hydroxide, insoluble. And you have more of this and makes more insoluble until you run out of the soluble magnesium nitrate. Now we have excess. Once all this is reacted and thoroughly converted into this base, you keep adding base, and that's what we call now excess. And the next drop, you will notice nothing happened. Will not form more precipitate, but the precipitate stays there. So no reaction, no further reaction, no further reaction with an excess of sodium hydroxide. What is your conclusion about this behavior here? That means that magnesium hydroxide is base, always base. It's base. It reacts only with the presence of acids, only to form the salt and water. You see, it's pretty different behavior as here. zinc hydroxide, the insoluble hydroxide of zinc 2 hydroxide, actually reacts with an excess of sodium hydroxide. That means it behaves, suddenly changed from this behavior base to acid to form a complex. That didn't happen to magnesium, no reaction. Now the next, so there's no formation of complex. Magnesium doesn't form complexes, and that makes sense because magnesium belongs to the black of the periodic table, so S black. Of the periodic table. Group 2 of the periodic table. What happened when we added ammonia to this precipitate? Did you notice any change? There was a formation of complex there. Any type of change? No, right? No reaction. All right, so conclusion, magnesium doesn't form metal complexes, and also magnesium does not have amphoteric properties. It's not an amphiprotic compound. The next reaction are the reactions of copper. This time we have copper as copper sulfate pentahydrated. Copper sulfate pentahydrated. This is the salt, and this salt is hydrated with 5 water molecules. That's why it's called pentahydrated. It's copper. Let me write it here, copper. Transition metal. So we have to write the oxidation number for that transition metal here in this compound. Remember, copper can work as copper 1 or copper 2, right? It's a transition metal, can have 2 different oxidation numbers. In this particular case, copper, in copper sulfate, copper is working with copper 2 plus oxidation numbers, so we have copper 2 sulfate. Penta, 5 hydrated. Has 5 water molecules in its crystalline structure. And that gives very interesting color. Do you remember the color of this solution? We make the solution with that. We have aqueous solution, and we get a nice blue. Oh, actually, it's the blue, right? Yeah, blue. Nice blue color solution. Crystals are also blue. So again, we have 3 test tubes containing copper sulfate solution. To each of the 3 test tubes, we added sodium hydroxide, a strong base, and what do you see? Precipitate on all 3 of them. Nice gelatinous precipitate. It's like a suspended, it's a suspension there. So what is the result? We have copper hydroxide, copper 2 hydroxide, which is solid. Plus sodium sulfate, which is aqueous. And the water, since this is aqueous, the water is there, right? That's why we're writing here aqueous. We don't need to write plus 5 waters. No, because this isn't water. It's a water system. When you add this to water, this becomes part of the solution, becomes part of the water. All right, so the point is it forms a precipitate. Copper 2 hydroxide is a solid. Here is a solid. And then to each test tube, to the first tube, we added hydrochloric acid. What do you observe? This is acid, and this is a base. So we have acid-base reaction. And that makes sense to think that that will form the salt, which is copper 2 chloride, Cl2, which is soluble in water, it's aqueous. Is copper 2 chloride plus water. Liquid. That water comes from this reaction. So yes, proof that the base, insoluble base, behave as such, as a base against the strong acid, forming the salt, copper 2 chloride, and water. As expected. In the next tube, we added an excess of sodium hydroxide. What happened? We added a few drops. It forms more precipitate. We added a few drops to this, to the first one. Because remember, in the tube, we added, in this tube, on this tube, we added a few drops of this. So we still have some extra of this soluble there and reacted. You keep adding this keeps reacting until at some point you added enough drops to match stoichiometrically the number of moles of copper sulfate you have there. After that point, there's no more copper sulfate. Everything reacted to form the insoluble salt. And now is when we talk about excess. Let's keep adding sodium hydroxide. Did something happen? Yes. What did you notice? The precipitate does not dissolve. Nothing happened. However, if you can watch the video again, notice that there was very little color change. The precipitate didn't disappear at all, maybe a little bit. And when that happened, you notice a little color change to a deep blue. That's because of the formation of another complex. Which is copper, OH, 4. And what is the charge of this? This is 2 plus. This is 4 minus. So we have 2 minus here, -2. And you can balance this with the spectral ions here. You want to see a nice, well-written equation? Well, you have to write here. This is Na2 plus two of those plus nothing, right? Because all the OH is reactive. Okay. And slightly soluble. Aqueous. And this one forms blue color. A little bit deeper. It's a different blue than this. This will be considered, this blue, lighter than this. But very, very small amount. And we check it. That's why initially we added a few drops of the excess of sodium hydroxide, and we didn't check it to see that formation. Once we check it, the different deep blue color disappear. In general, we can say that these hydroxides are insoluble. If you add an excess of sodium hydroxide, they are insoluble. However, it can form a very tiny amount this complex. In the next experiment, we added to the third tube ammonia. What do you observe? You observe the formation of another complex. Now this time it turns right away into a deep blue solution, forming a complex copper NH3 4 2 plus. Because ammonia has no charge, it's neutral. So this charge belongs to the charge of copper ion. Copper 2 complex. And that's called tetraamine copper 2. Tetra 4 amine copper 2 complex. Deep blue, very nice deep blue color. Prussian blue. This proof is soluble, right? The precipitate disappear. Yes. This proof that copper can form complexes. However, copper doesn't have amphiprotic property. Doesn't have amphoteric behavior. So those are the equations I was mentioning during the lab. They are not in the handout. All other reactions are there. All other reactions, I'll find them there in the handout, in the lab manual, except this. These reactions weren't there. I didn't do the last part of the experiment talking about the copper sulfate pentahydrated salt. This compound, since it has water, shows the blue color due to another complex, copper complex, which is copper H2O6 2+, and this one shows a deep color blue, deep blue, deep blue color. That's why this compound has the blue color, because these copper ions in the crystalline structure forms complex with the water. Very tiny amount, giving this color there. Now, and this is called, I mentioned it before, the pentahydrated, the hydrated form. This part of the experiment consists on getting rid of the water by heating. When we heat the blue crystal, we add heat enough to remove the water from here to form the copper sulfate solid crystal. The color of this is like white. And this is what we call the anhydrous. White anhydrous copper sulfate. I mean, anhydrous means no water. No water. As opposed to hydrated. Hydrated means with water. So we call copper sulfate pentahydrated with water, and this is copper sulfate anhydrous. You see no water here because the water was evaporated using heat, using the flame. I didn't do this part because I did the This demonstration is in the chloride,
cobalt chloride. As you can go back, watch the video, and notice that I did that demonstration of hydrated and anhydrous, and I mentioned it. Similar situation. We have hexahydrated cobalt chloride compound. We have then, when we heat it, we get the anhydrous one. Do you remember the color of the hydrated cobalt chloride? Check the video. And what's the color once we get rid of the water out of the crystalline structure to get the anhydrous cobalt chloride? So you see similar situation here. That's why I didn't do because I already mentioned it in that part of the experiment about the hydrated forms and anhydrous form. All right, so I'm going to stop here. Again, if you have questions, send me an email. Let me know you like those recordings. I'm going to stop here. And again, I'm going to start making recordings and post it on the Blackboard, and I'll give you details on through the announcements. Always read the announcements every time. Check every week to see if there's no announcement there. All right, so see you next time.